So the recording started, and let's wait for maybe 1 or 2 minutes. I think people are still, participants are still trickling in.
Okay, sounds good.
Okay, so it looks like the influx has slowed down, influx of participants, and it is already 1 p.m. Here in Texas College Station. So let's start, and it is my great pleasure to introduce Dr. Saxena, who graduated from University of Delhi from a group of Professor Samit Mandal. And since then, she already had pretty distinguished career. In fact, she was a Marie-Curie Fellow in Poland, in University of Warsaw. And also now she's a postdoc at Ohio University, working in a group of Dr. Meisel since December of 2019, and making a lot of progress. And that the subject of today's discussion is, as you can see on the screen, mapping nickel 56 bypass in the RP process. So before we begin, let me inform you that everyone is muted and you cannot really unmute yourself. But if you have short question during the presentation, then either raise your hand or ask your question using chat. And if not, then wait until the end of the presentation, at which point I will unmute everyone and you will be able to, I will allow you to unmute yourself, and then you will be able to ask questions, right? Okay, at this point, Mansi, the floor is yours, so please start, and good luck with your presentation.
Thank you, Gregory, for the nice introduction. And thanks for inviting me for this seminar here. So as you already mentioned, I'm currently working as a postdoctoral research associate at Ohio University for the past 1 year. So in my seminar today, I would be highlighting some of the results which we have obtained in our recent experiment at NSCL that was performed. With the motivation of constraining the 56 nickel bypass in the RP process. So moving forward, let's see, so what's in the agenda for today? So this would be the outline for my presentation. So I would begin with a brief introduction about X-ray bursts and talk about the waiting points in the RP process. And how this actually formed the motivation for our recent experiment at NSCL. I should also add here that this experiment was actually part of a beta-decay campaign that was performed early last year. Finally, I would discuss the analysis which we have done and the exciting results which we have obtained. So, so the X-ray sky, as we see, is always alight with activity. And if you could view the night sky with X-ray sensitive eyes, you would see a turbulent sky filled with all kinds of X-ray emitting objects like dying stars, quasars, etc. Now, this is an animated video which was released by MIT. It's actually 2 decades old, but it's still interesting. So it actually spans about 4 years and shows the ever-varying turbulent nature of the X-ray over these years. Now depicted here are X-ray emitting objects on the map of our entire sky. They're marked here by a circle, so the bigger the circle, the more brighter it is. Now the most prominent ones are actually the X-ray binary systems. Now one such marked here is Scorpius 1, which is the brightest X-ray source in our galaxy. which was later identified as a accreting neutron star. Now, the most earliest of these discoveries in this direction, they were pioneered by Riccardo Giacconi and his research team in the early 1960s. For his work, he also received the Nobel Prize in Physics in 2002 and is very aptly called as the father of X-ray astronomy. He was also instrumental in giving the first model for a binary star system and how actually the neutron star in orbit with a low mass companion star can accrete material. And when they are actively accreting, they are some of the brightest X-ray sources in the sky. That's a picture of him receiving his Nobel Prize in Stockholm. Okay, so what does your accreting neutron star system look like? We have a neutron star in orbit with a radially massive companion star. Now, the neutron star has a mass of about the solar mass, but it has a radius of about 10 to 15 kilometers. Now, stars in a binary system, they are close enough to permit mass transfer. Now, the normal star has essentially filled its rose globe, which is its gravitational sphere of influence, and that allows mass to transfer from the companion star to the gravitational sphere of this neutron star. Now, the solar type matter flows and forms an accretion disk surrounding the neutron star and ultimately piles on the surface, forming an envelope. Now, eventually, this layer becomes so thick until it reaches high temperature and pressure conditions such that nuclear reactions begin in this layer, heating the entire layer. Now, this additional heat increases the nuclear reaction, leading to a runaway thermonuclear explosion on the surface of the neutron star, which we typically call as the type 1 X-ray bursts. Now, type 1 X-ray bursts are the most frequent types of thermonuclear stellar explosions in the galaxy. They are powered, as I said, by thermonuclear runaways on the surface of the accreting star. Now, here I have highlighted some of the basic characteristics of X-ray bursts. Now, the X-ray output from these bursts, they are a factor of 100 to 1,000 more brighter than normal optical luminosities. They can have X-ray output greater than 10 to the power 34 ergs per second, having typical accretion rates of 10 to the power minus 9 to 10 to the power minus 10 solar mass per year, with reaching peak temperatures of about 1 to 2 gigakelvin and densities of about 10 to the power 6 gram per centimeter square. Now, up to date, more than 100 X-ray burst sources have been discovered. Now, thinking of this in a very bigger picture, why are we interested in studying X-ray bursts? Now, these X-ray bursts can act as astrophysical probe to study the properties of neutron stars. Neutron star masses and radii, they help constrain the properties of matter at a level of nuclear density. Now, the main direct observable measured from X-ray burst are the X-ray burst light curve. Now, these, of course, are detected by X-ray telescope. These are massive satellites which are floating in the sky to detect these X-ray flashes. Now, many different have been used in the last many years. For example, Exosat, Chandra, which I show here, and etc. These telescopes, they record the timing of these X-ray flashes and also the energy output. Now, on the right, sorry, I have a figure. So here is a X-ray burst light curve from the very first observed X-ray burst. So normally, as we can see that these bursts, they are characterized by fast rise time between 1 to 10 seconds and having a burst durations lasting from 10 to 100 seconds. So now coming to the nuclear physics aspects, which are responsible for the ignition of the thermonuclear runaway and the nucleosynthesis process, which is initiated during the cooling phase of the X-ray burst. Now, since the accreted material is hydrogen rich, the initial burning is dominated by the PP chain and the CNO cycle. Now, as the energy generation rate here is temperature independent, this is basically called as the stable part of the burning, heating the entire envelope and turning it into helium. Now, as it's the stable part of the burning, these reactions do not really result in a thermonuclear runaway. So the explosive nuclear burning is actually triggered as soon as temperature sensitive reaction sequence like the triple alpha reaction, they start to contribute. Now at around temperature of around 0.7 gigakelvin, it's the breakout reaction from the hot CNO cycle that is initiated or started. So this is initiated by the 15 oxygen alpha gamma and 18 neon alpha P reactions. So now while the triple alpha reaction delivers the CNO's fuel, essentially, the breakout reactions, they can open door for two long reaction chains. So first is the alpha P process, which is a series of alpha P and P gamma reactions. These are essentially fast reactions and take place at the onset of the burst. This process ultimately feeds into the RP process, which is a series of rapid proton captures interspersed with beta decay reactions. Now, because of the higher peak temperatures that can be achieved during the energy release due to the RP process of around 1 to 2 gigakelvin, the RP process can extend all the way into E equal to 100 region, where it ultimately ends into the tin antimony tellurium cycle. But I should add here that ultimately the length of the reaction chain depends on the amount of hydrogen that is still present and also on the maximum temperature that has been reached. Now, all these different processes, they shape the different parts of the X-ray burst light curve as depicted here. Now, the rapid proton captures, they are the main process driving the nucleosynthesis along the proton tripline. Now, in this nuclear chart displayed here, these black lines connecting all these boxes, they represent the nuclear reaction rate. The gray boxes are the stable nuclei. Now, the path of the RP process lies between the line of stability and the proton tripline and is determined by a competition between the charge particle reaction and the beta decay reaction. Now, at low temperatures, both these reaction rates are comparable. So the RP process will run close to the line of stability. But at higher temperatures, the P gamma reactions occur more rapidly than the beta decay reaction. And hence the reaction path will now run closer to the proton tripline. So now further processing to heavier elements can be essentially delayed or temporarily stalled when you may reach a waiting point nucleus, for which the further proton capture is inhibited and the reaction flow needs to wait to proceed further. Now the reason for the inhibited proton capture is the small q value, because of which the resulting proton capture becomes smaller, and then the reverse photodisintegration rate process at higher temperature also comes into play. So this eventually leads to the P gamma and gamma P equilibrium. So naively speaking, what does this mean? That the reverse reaction rate is now comparable, so that it will quickly remove the proton that was just added, inhibiting further proton capture and essentially delaying the reaction flow. So typically nuclides with either negative or small values of the P gamma Q values, and also relatively having longer beta decay half-lives, these are referred to as waiting point nuclides. And of course, the speed of nucleosynthesis to heavier elements and also the shape of the light curve is now determined by the total lifetime of these waiting point nuclides. Now, another way, a simpler way to think of these waiting point nuclides are that these are those which do not have a swift destruction process, and this can bring most of the energy generation to a standstill, delaying the nuclear flow, which eventually impacts the final abundances of the elements. We can try and understand this in this simple schematic diagram. So where this pipe, it demonstrates the nuclear flow or the reaction rate in the process. And the amount of material in each tub is the abundance of the element produced. So if a waiting point nucleus lies in the reaction path, it results in a weak reaction flow. So typically like a tap being switched off, and the nuclear flow is essentially delayed to heavier elements. So now to have a more quantitative definition for a waiting point nuclei, The photo disintegration rate and the proton capture rates can be related by this Saha equation, where mu reduced is the reduced mass for the P gamma reaction. Now, under typical X-ray burst condition, and in case of a P gamma, gamma P equilibrium, this equation is satisfied for Q values around 1 MeV. Now, the major waiting point nuclides which satisfy this equation and have also substantially longer half-lives are marked here. Also additionally plotted here are the abundance evolution during the hydrogen-helium burning at a constant temperature. Now, the time evolution of the most abundant waiting point nuclide are shown here, and it clearly marks, we can clearly see that 56 nickel has the maximum abundance. So 56 nickel is actually one of the most dominant of waiting point nuclides. And historically speaking, it was actually also thought to be the endpoint of the RP process. Now, interestingly, for waiting points which are lying away from the proton drip line, there can be possibility of material flowing around the waiting point. Now, we know that 56 nickel, where all the experimental constraints suggest that it's a strong waiting point, but it may be possible to bypass this 56 nickel waiting point at high temperature and densities. So this was actually the crux of motivation behind our experiment. So recently, bypass around this 56 nickel point has been suggested and pursued. Now, the alternate reaction path breaks out at 55 nickel and follows the reaction sequence through proton capture to 56 copper and 57 zinc, hence completely bypassing 56 nickel waiting point. Now, the breakout reaction, that is the 55 nickel P gamma, this determines the branching at 55 nickel into this alternate bypass scenario. Now, a recent precision mass measurement on 56 copper has constrained this 56 nickel P gamma reaction rate to within a factor of 2. Now, even with these available or even with these constraints, there remain additional nuclear physics uncertainties that can affect this alternate reaction flow. So namely, the proton capture rate on 56 copper is needed, which would determine the flow through to 57 zinc. But ultimately, the major dominant uncertainty for this bypass is whether 57 zinc beta decays to 57 copper and increases its equilibrium abundance, or 57 zinc beta delays and emits a proton and essentially repopulates 56 nickel. So that is why the 57 zinc beta P ratio is actually one of the crucial ingredients to map this bypass. Now, till date, there are two measurements for the beta delayed proton tranching ratio of 57 zinc. So this recent one was actually published just during our experiment. Now, the effect of the variation of the present uncertainty in the zinc beta P ratio is actually shown here in this phase space diagram, which essentially shows the fraction of the reaction flow that bypasses 56 nickel as a function of temperature and density. So now, considering a maximum favorable condition, that is taking a 3 sigma lower bound for this branching ratio, we can see that 56 nickel is significantly bypassed of about to 40%. And in the minimum favorable case, if I take 1 sigma upper bound, that is essentially 100% of branching ratio, effectively there should be no bypass. So now this picture needs to be better constrained. And so that is why this actually formed the motivation of our current measurement to have a better or high precision value for this proton branching ratio. So moving forward to the experiment. So before moving on to the experimental details, I would want to share a few details about beta spectroscopy. So this is the nuclear chart. Most nuclei which we know are beta unstable. So they either decay by beta plus or beta minus. Now, from the study of these beta decay reactions, we can essentially obtain rich spectroscopic information. Now, in a beta decay reaction, the decay is usually followed by the emission of a particle and or gamma rays. So now when you are closer to the proton or the neutron drip line, we can also have a possibility of particle emission as the Q values here are pretty large. So on the neutron rich side, we might have beta delayed neutrons, and on the proton rich side, we will have beta delayed protons. So as we know that zinc is a neutron deficient or a proton rich nuclei, so essentially it would emit beta delayed protons. Now on the right, I have a schematic of what we can expect in a beta delayed particle emission experiment or reaction. So we have the parent nuclei, which undergoes beta decay, and then some states are populated in the daughter nucleus. Now the energy available for this reaction is the Q beta value. Now the states that are populated in this daughter nucleus, they can be either above the proton separation energy or below the proton separation energy. So if it's below the separation energy, these will essentially decay by emitting gamma rays and decay to the ground state of the daughter nucleus. But if they are above the separation energy, then it can decay by particle emission, which we call as the beta delayed proton emission. It is called delayed because it has to wait for the beta decay to happen first. So in this case, we call this parent as the precursor. The daughter is called the emitter, as it emits the proton. And then we have the beta P daughter. Now the energy of the proton, it's essentially equal to the Q value minus the proton separation energy. Now using this beta decay spectroscopy experiments, we can have information which can be of great interest to both nuclear structure and also nuclear astrophysics. So highlighted here are some of the information which we can extract from such experiments. So of course, we can have accurate value of half-lives. We can have information on ground state, masses, and spins. If we can identify individual particle groups and gamma rays, we can have information about the particle decay branching ratio, beta feedings. Using these, we can go ahead and reconstruct the partial decay scheme. We can have information on the isobaric analog state. Essentially, all these nuclei which are proton rich, they also lie on the RP process path. That is why we also have this nuclear astrophysics interest. And finally, we can extract the absolute values of the Fermi and Gamow error strengths. So moving to the actual experiment, the experiment was performed at NSCL last year in March. So the primary beam of 78 krypton was initially accelerated to about 150 MeV per nucleon, having a charge state of about 34 plus using this coupled cyclotron facility. The primary beam then hits the production target, which was 9 beryllium, and it undergoes projectile fragmentation. Now, the electromagnetic separation based on the magnetic rigidities was performed by the A1900 fragment separator. Now, the A1900 fragment separator, it has 4 dipole magnets and 24 quadrupole magnets, which is used to select the ion of interest. As zinc 57 is a more exotic nuclei and lies on the proton rich side, as I've already mentioned, we had to use a secondary filtration using the radio frequency fragment separator. And finally, the secondary ion beam was transported to the S2 vault area. Now, the principal detector system was the NSCL beta counting station. Now, shown here is the schematic diagram of our experimental setup. So in the upstream, we had 2 pin detectors of identical thickness, followed by an aluminum foil of 0.5 mm thickness, which was used as an energy degrader. Now, the 57 zinc ions were implanted in the double-sided strip detector, having a thickness of around 500 micron. Now, this DSSD, it had 40 cross 40 strips of 1 mm each, vertically and horizontally, ultimately resulting in a pixelation of 1600. So they were used to measure the energies, time, and position information for both the implant and the decays. Now, as the energy ranges for the implant and the decays are quite apart, so one being in the GeV range and one being in the MEV range, as a result, we had to use two different gain settings. I should add here that the thickness of the pin detectors and the aluminum foil was actually chosen so that we would be able to centrally implant the zinc ions in the DSSD detector. Now, the beta counting station was surrounded by 16 Clover detectors. These were part of the Clover share campaigns. These detectors were used to detect the beta delayed gamma rays. Now, here are some snapshots from the experiment. So these are the pin detectors which were placed upstream. That's actually the entire setup, but mainly showing all the Clover detectors from the Clover share array. That's the BCS stack, which was actually put inside this. And that's a zoomed up picture of the DSSD detector, which went on top of this beta counting stack. And this was put inside here. So moving on to the analysis, which we have performed. So foremost, the particle identification was performed using the standard delta E and TOF method. The time of flight was actually the time difference between the pin detector and the scintillator, which was placed at the extended focal plane. The energy loss was also obtained from the same pin detector. Now, as seen in this PID matrix, we could clearly isolate 57 zinc, which was our isotope of interest. This gap here corresponds to all those isotopes which were actually kicked out using the RF clicker. So the A1900 group did a very good job with the beam. And in total of 3 days run, we could obtain around 13K zinc implants. So when a 57 zinc nuclei decays, it may emit a beta particle or a beta plus a proton, as I said. So now the protons and the beta particles, they are simultaneously emitted from the site of the implantation. Now, since the betas usually escape the implantation detector by depositing only a fraction of their energies, pure beta decay events actually contribute to the mostly low-lying part of the spectrum, or low energy part of the spectrum. Protons, on the other hand, are stopped inside the DSSD and deposit their full energy. So as the Q value of the decaying system are of the order of several MeVs, the majority of the beta particles, they are minimally ionizing and leave only a fraction of their energy inside the DSSD. Since their spectrum is a continuum spectrum, so this essentially produces a tail on the right-hand side of each proton peak. Now, in our measurement, the measured energy in the DSSD detector was always the sum of the decaying energy of the proton and the residual energy of the betas. Now, this feature is known as the beta summing feature. Now, as a result of this, even though we had 100% efficiency for proton detection, the resolution was quite degraded. So in our case, we used a thorium source for initial calibration. And with that, we had about 60 to 70 kV FWHM for the 6 MeV peak. So this is essentially the charge particle spectra which we have obtained for the decay of 57 zinc nuclei. This was collected for 10 half-lives after the 57 zinc implantation. So all the events below 900 keV, they are pure beta decay events, and everything above is beta delayed protons. We could identify different proton groups, which I have marked here on the spectrum. Now, the main and the foremost aim of the analysis is actually to correlate the decay events with the implant, that is 57 zinc. So this is actually achieved by examining the relative time and position of the implant and decay events. Now, 57 zinc is once it is implanted inside the DSST, we can localize its position and time. So once we have localized the pixel of the implantation, we can look for the decay events that happened uh, within a bit of tolerance, which we define as by this correlation matrix. So this correlation matrix basically consists of the nearest neighboring pixel. And all this business of correlation is done within a fixed correlation time window. This correlation time window is usually adjusted from isotope to isotope and is usually taken to be much longer than the half-life of the nucleus. So coming to the exciting results which we have obtained. So now shown here is the decay curve, which we have obtained by histogramming the time differences between the implants and the relative decay events. So now, while obtaining these decay curve, we actually imposed an additional condition, that is to select only proton decays. Now, this was actually achieved by setting an energy threshold in the DSST by choosing only the beta delayed proton decays. The advantage is that the daughter activity where no protons are involved or are present is actually removed from the correlation time spectra. So in this way, this half-life can be simply fitted by the parent activity. So in our case, we had set the correlation time window to about 3 seconds. So this decay curve was fitted with an exponential decay function having a constant background. I should add here that of course, due to the high pixelation of the DSST detector and the low implantation rates, the background was sufficiently low. So this is the value of half-life which we have obtained, 43.63 plus minus 0.8. It's in very good agreement with this previous published value, though in slightly bit of tension with this recently published value. But of course, our result is much more precise. So now to the one of the most important results, which we have important value which we have extracted. So assuming 100% DSST efficiency for both proton and implants, the total proton branching ratio was obtained by comparing the number of total implants with the number of observed protons above 900 keV. So the proton branching ratio, which we have determined from our experiment, is 84.7 with a very small uncertainty of 2%. So again, I should add here that it's consistent with all these previous literature values, but we have successfully done what we wanted to do to have a much higher precision for this value. Now, the gamma ray spectrum for the decay of 57 zinc has been measured for the very first time. So now shown here is the beta delayed gamma spectra associated with the decays that were correlated with the zinc implants. Now, interestingly, this gamma ray spectrum which we have obtained was quite rich, and we could actually observe some low intensity gamma ray transitions. This is the expected 511 keV. Now, to look for the origin of these gamma ray transitions and to be able to place them inside our decay scheme, we went ahead and constructed proton gamma coincidences. So what I show here is an example. So if we gated on one of these proton peaks, this is the resulting gamma ray spectrum which we obtained. So clearly one of these gamma rays at 2 MeV immediately pops out. Now, a second cross check just to make sure that this gamma ray belongs to the decay of 57 zinc. The half-life was also extracted by gating specifically on this gamma ray transitions. So that's the spectrum which we have obtained. So of course, the statistics were quite low, which was expected. But we have obtained a half-life value, which is comparable to what we have obtained from the beta implant correlations. So to give a complete picture, so these are the proton gamma coincidence spectra, which we have obtained in our analysis. So once more, this is the charged particle spectra, and by imposing gates on the various proton peaks, which I label here, we obtain these gamma ray spectra. So just for easy understanding, it's color coded. So if we gate on this green peak, we see all these green gamma ray transitions in coincidence. If we gate on this yellow peak, we see this transition in coincidence. No coincidences were observed for all these higher lying, higher energy proton peaks. So these proton gamma coincidences, which we have obtained, they were essentially used to construct the level scheme. So as now we can see that which gamma is in coincidence with which proton peaks. So once more, zinc 57 beta decays to 57 copper. Now as the proton separation energy, it's quite small here. All these states above are particle unbound, and they decay further by emitting a proton. These protons are essentially feeding 56 nickel nuclei. Now, since the energies of these gamma rays are unique, and based on the difference of the energy levels in 57 copper, we can go ahead and place these gamma ray transitions. So I show an example here. So I place the gamma rays, which are de-exciting from the isobaric analog state. And we can quickly see that these gamma rays are feeding states which are above the proton decay threshold, and hence they further decay by proton emission. So hence what we have observed here is a more exotic decay branch, which we call as the beta delayed gamma proton decay in the FP shell nuclei. We could observe this for 3 different branches. Now, this is the complete decay scheme for 57 zinc, which we have obtained. Now, since we also see these gamma ray transitions in the decay of 57 zinc, it is essential very much to also estimate the intensities of these gamma rays. Important thing to note is that the proton intensities now need to be also corrected for the intensities of these feeding gamma ray transitions. So for example, if I want to properly account for the beta intensity for the isobaric analog state, in addition to the proton intensities, we also need to account for these gamma intensities. So the beta feeding to the isobaric analog state was determined to be around 49%. And the corresponding log FG value was 3.37, meaning essentially it's a super allowed transition. The rest of the beta feedings is mentioned here for the rest of the energy states. Now, I also went and checked the decay scheme for the mirror nucleus of 57 copper, that is 57 nickel. Now, due to charge symmetry, we should expect a similar decay scheme in this nuclei also. So this 7.5 state at 5238 keV in 57 nickel is the isobaric analog state corresponding to the 5297 keV in 57 copper. Now these de-exciting gamma rays at 2.6 MeV and 2.0 MeV, they are similar to the de-exciting gamma rays which we have obtained or which we have seen in 57 copper. Though we are currently limited by the extent of the experimental data available, we can still satisfy ourselves by the striking similarities in the gamma ray transition we see from the de-excitation of the isobaric analog state in both nuclei. Now there is yet another surprise in this nuclei. Now any beta decay process that is taking place is characterized by either a Fermi or a Gamma-Teller transition. Now the super allowed Fermi transition is proportional to the isospin raising or lowering operator tau, and the Fermi transitions connecting these states which have the same isospin, which we essentially call as the isobaric analog state. Now, isospin symmetry prevents any fragmentation of the Fermi strength, and the sum rule should be exhausted by the single isobaric state. So considering isospin symmetry, the Fermi strength of this isobaric transition should be equal to 3. Now, interestingly, the experimentally calculated value from our analysis, considering the half-life and the intensity we have achieved. So the Fermi strength comes out to be 2.63. Also, additionally, in our experiment, we have observed both proton emission and gamma decay from the isobaric analog state. Now, I should add here that de-excitation by proton emission from the isobaric analog state is actually isospin forbidden. This only happens if the isospin symmetry is being violated. So this scenario can be explained only by the concept of isospin mixing. So we went ahead, and what we have done is we have used a very simple two-state model where our isospin non-conserving part is added to the nuclear Hamiltonian, which will cause this analog state with isospin equal to 3½ at 5297 keV to mix with the closely lying anti-analog state at 5.16 MeV, having an isospin equal to 1/2. Now, in the first order perturbation theory, the isospin impurity is the ratio of the mixing matrix element and the difference in the energy levels. Now, from the reported energy difference between these two states, the mixing matrix element was calculated. So this comes out to be 21 keV, and the unperturbed energy spacing comes out to be 121 keV. We went ahead and we have estimated isospin impurity to be about 3% for this nuclei. We also have interesting shell model calculations. They are currently ongoing, and they are being performed by Nadia Smirnova from CNBG, France. So now, as 57 zinc, I said, has isospin equal to 3½ it forms a member of the isobaric multiplet of having a dimension equal to 4. Now, the analogous energy states having same isospin should also have the same mass excess value. But however, the electrostatic effects perturb the energies of these nuclear analog states, hence breaking this degeneracy. Now, in the first order, the mass excess as a function of the isospin follows this quadratic equation. Now, we have used this IMME equation to extrapolate and calculate the mass of 57 zinc. So the mass excess value for 57 nickel and cobalt, they were picked up from the AME database. The mass excess for the IES state and 57 copper was corrected, taking into account the isospin mixing, and all these were incorporated in the FIT. So plotted here is a comparison of the predictions of the mass excess for 57 zinc. So this is from the AME database of 2016. This is a recent publication which has come out last year. So they actually use local mass relations between mirror nuclei and kind of project the value for the mass excess. And this is our newly constrained value, which we have obtained from the IMME FIT. So of course, all of them are pretty much in agreement with each other. So coming to the astrophysical result we have in hand for now. So we were able to constrain the 56 copper P gamma reaction rate based on the new zinc 57 mass, which we have obtained. Now, since the level density within the gamma window for 57 zinc was not very high, the proton capture actually proceeds through the few isolated resonances. So the rate can be approximated by this formula. So it's essentially the summation of the contribution due to each of the resonance. And it has a dependence, of course, on the resonance strength and the resonance energy. So the resonance energy was calculated for the levels using the updated Q value for this P gamma reaction. Now applying this new Q value and taking 1 sigma uncertainty, we could constrain the reaction rate to within a factor of 2. For comparison, I also have the reaction rate for 1 sigma uncertainty from the EME, calculated using the Q value from the EME database. So what's next in line? So next, we want to study the impact of all these new ingredients on the 56 nickel bypass in the RP process. So as I speak here, Wasia is already performing these reaction flow calculations for us. So the main idea would be to actually see the effect on the reaction flow around the 56 nickel waiting point, and considering all the new constraints which we have in the nuclear physics uncertainties in this region. I should also add here that the initial preliminary results which we have in hand, they clearly show us that we are able to constrain this 56 nickel bypass with much smaller uncertainties. So hopefully we should have all the results very much soon available. So to finally summarize, Zinc 57 beta delayed experiment was performed at NSCL in early March in 2020. We obtained a precise value for the half-life. We also obtained the zinc beta proton branching ratio. We went ahead and constructed the partial decay scheme for 57 zinc based on the proton gamma coincidences. We could observe a more rare and exotic decay mode, which is the beta delayed gamma proton decay. This is probably seen for the second time for any FP shell nuclei. The 56 copper P gamma reaction rate was constrained using the new mass excess value for 57 zinc. And of course, we plan to go ahead and see the impact of these all these new ingredients on the 56 nickel bypass. In addition, we also have, as I mentioned, the shell model calculations ongoing. So hopefully we would have the draft very soon out for all these nice results which we have obtained. A big shout out to all the people who have contributed in many very different ways for the successful completion of this project. I thank you all and thank you for the attention.
Right. Thank you very much, Mansi. This is an exciting result indeed. So now it's time for questions. So I'm going to allow everyone to unmute themselves and just a second. And please raise your hand or use chat. And you should be able to unmute yourself also. Now. So
yeah, I have a question.
Please, yes.
Yeah, very nice experiments, and I enjoyed the talk. I missed something in your discussion of the proton decay. You discussed the isospin admixtures, but you didn't discuss the large spin differences. So you have low energy protons and large spin differences between emitter and the final state. How do you calculate the transmission coefficients?
Okay, so yes, you're right. So as 57 zinc it decays, so these protons, they are feeding the ground state and also the 2+ state for 56 nickel. So we would have like L equal to 1 feeding the probably the ground state, and L equal to 3 feeding the 2+ state. So so what's your question? How have we estimated the you mean like the proton widths?
You have spins of 7 halves, and so connecting lines to very low spin 0 and 2+. Okay, so how do you do that with a 2 MeV proton?
Okay, so for calculating the proton widths, what we have done is we have picked up the already available shell model calculations which were done by Fisker. And what we have done is
that's the structure, not the decay. You need a transmission coefficient through the barrier.
Yes, right. Okay, but okay, we haven't as of yet done that calculation, so maybe I'm missing that part.
So that may be a major issue there.
Okay, so that's something I have to think about. Yes.
Okay, I see a raised hand. Philip, please unmute yourself.
Hello, can you hear me?
Yes,
hi,
yes, we can hear you.
Great, fantastic. So I have a kind of related question, which was you were saying about the using the for this mixing where there's mixing between the T3 halves and the T1 half states. And I was wondering whether it was possible to say anything about the mixing from the proton decays, and I guess that's still a work in progress if you're trying to calculate the decay widths. Having said that, it is possible to do them analytically. There's various, or numerically, there's various tools for it. But I wonder if you're planning to, I suppose my question is then, are you planning to try to make a consistent picture between the beta decay strengths, the proton decays, the gamma decays, kind of try to do it holistically? Or
Yes, okay, so we haven't taken that route of doing it analytically. So we were hoping that we might have some more insight by these shell model calculations where you can like actually define all these values. So yeah, we have right now taken that route, but okay, I'm probably also not aware of the tools which are very handily available to make a quick calculation.
Or you could use WKB to make some estimates.
Yeah, that's right. Okay, yeah, we can think about that.
thanks.
Okay, more questions? So Mansi, actually have one. So you show a nice proton spectrum which follows the beta decay, but it has relatively limited energy resolution. So how sure are you that those peaks that you observe actually belong to one state and not the doublet or
Yes, that's a very valid question. So so actually in our experiment, yes, we had a very degraded resolution. So what we have done is that there is an earlier publication where they have studied the zinc 57 beta decay, and they had a different type of detector. They were not having a DSST detector, but like a delta E detector. So it was like a gas detector followed by a silicon detector. Yeah. So there they had like an energy resolution of about, if I'm not wrong, maybe 30 keV, and they could do a very nice proton spectroscopy. So what we have gone ahead, like used their relative intensities and applied it to our data.
Okay, I see. All right, that's
Yeah.
good. Okay, more questions? Okay, if not, then let's thank our speaker virtually, and thank you everyone who joined our seminar series. And don't forget that the next one is February 4th, and we'll have another very interesting, exciting presentation in 2 weeks from now. All right, thank you and goodbye.
Thank you.